In this video, we're going to look at the forces that affect an object on a ramp or an inclined plane. And what we'll do is we'll break those forces up into their components so they become more useful for figuring out if this box would first, say, accelerate down the ramp, or would it stay on the ramp, or something along those lines. This video is intended to be kind of a helpful reminder of how to find these forces if you have problems that pop up with these type of problems later on. So to start with, we have to basically define some things. And the first thing we have to define is that this box has some mass m, and we're going to work with variables in this video to make it a little bit more general. So m is the mass of the box. Sorry about that, I had to clean some things up there. And then what we're going to do is just start thinking about, okay, what are some of the forces that are affecting this? And one of the forces that are affecting this is gravity. And gravity is going to be basically pulling this straight down. And then hopefully from prior videos, remember, okay, well, gravity gives this box some weight. So we could say, well, the force of gravity is equal to the weight of the box, which would be equal to mass times gravity. So we can say that this red vector pulling this down in this direction is equal to mg. At this point, there's really one other force that you could probably remember that might be affecting this, and we would call that force the normal force. If you kind of remember, if you have something on a flat surface, like a box, that there's two forces that really affect any of those things. Here's my box and the surface, and those forces are the gravitational force, again, that pulls it down, which is the weight, and working against that is the force of the table, or what we would call the normal force. And when it's a horizontal surface, the weight is equal to the normal force. But this is not a horizontal surface. We have something that's sloping. So part of this force is pushing it down against the surface, but part of it is also pushing it along the surface. So there's two different components to this. So what we need to do is find what those things would be. So we know that there's going to be a component that goes this way, and another component of this that's going to push it that way. Or we could put that up here and push it down the ramp. Right now I'll even move that up here, but we'll slide that back down there later. So we're going to call these things the perpendicular force, F perpendicular, and the parallel force, F parallel. The part of this force that's pushing it down the ramp, the part of this force that's pushing it into the ramp. So the normal force in this case, I'm going to just put a little vector here, and I'm going to make it dash. This one's a little bit different. Would be the opposite of this perpendicular force. So this over here would be what we would normally label as our normal force. But we need to have some kind of angles in here. We need to have some understanding of what's going on in this. So what we need to do is use some geometry to get an understanding and be able to figure this out. So the next thing I'm going to do is kind of show some old ideas from the geometry class and say, okay, if I have two parallel lines and I then cross those parallel lines. Now these are dashed, that doesn't really matter. But the idea is, if I know this angle here, I also know this angle here. These two angles must be the same. They're identical because of the idea of alternate interior angles of parallel lines that are being crossed by another line. So we look over here for a place where that's happening. If I kind of switch colors, here's a parallel line and here's a parallel line, and not to get too much color on here, we know this angle here is 90 degrees. Sorry about the bad drawing, but that's 90 degrees here. If this is theta, this is 90, the total of all three of these angles must be 180. Well, I can subtract 90 from that right away. So this angle here would equal 90 minus theta. So, okay, well, now I want to look for my other system. If I know this is 90 minus theta, I can now say, all right, well, then this right here would also be 90 minus theta. Because again, we have a parallel line here, parallel line here. This was drawn perpendicular to the surface. So now the question is, what is this angle? We're just going to call this x, and we'll clean that up a little bit later on. But we want to know what that x angle equals. So, in this little triangle up here, all the angles have to total 180 degrees. So I have angle x plus angle 90 minus theta plus the 90-degree angle. So this is just simple algebra. I can take 90 from both sides. I'm sorry, I can subtract 90 from here, which is really like subtracting 180 over here, because 90 plus 90 is 180. Basically cancel that off, I end up at 0 is equal to, cancels off, x minus theta, which then, okay, I want to move that to the other side. Theta is just simply equal to x. Now that is very valuable. So again, to clean this up over here, I'm just going to take my eraser tool and kind of get this out. We basically isolated this top angle and figured out that it's equal to theta. Okay. So now what we need to do is say, okay, using simple geometry, we can figure out this perpendicular side and this parallel side. So I'm going to go back and I'm just going to simply move these things back down so you can kind of see how the triangle forms again. So if I take this, try to take that and move that again, put that down here, now we can see the two different sides that we're trying to find. Move that down there at the bottom, and I'm going to try to get rid of a bunch of this so we have more room to write. So we're in the home stretch. We're trying to find out what these two things are in terms of their symbols. So because this is a right triangle, and again you can kind of see that part here, we can use our good old SOHCAHTOA or our trigonometry functions. We'll find the perpendicular side first, which when you look at theta, this is the adjacent side compared to theta, which would be our cosine function. So cosine theta is equal to the adjacent over the hypotenuse, which is going to be cosine theta is equal to the adjacent side, f perpendicular, over mg, and then solving for the perpendicular side, right, the perpendicular, mg cosine theta is equal to that perpendicular side. Now, the other side, this parallel side, is going to be our sine function. And that's going to equal the opposite over the hypotenuse. So again, plugging in our symbols, sine theta is equal to f parallel over mg. And solving again for f parallel is going to equal mg sine theta. This one's probably the more useful, the one you're going to use more often than not, because that tells us how much force is actually pushing this down the ramp. And if we know what the frictional force might be, maybe there's like, let's say 5 newtons of frictional force, and we know that this, if we knew what the mass was, we could calculate the horizontal, or not the parallel force pushing it down the ramp. We can see if it's enough, if the frictional force is more than 5, if the horizontal, the parallel force, is more than 5, it would move down the ramp. If it was 5 or less, it would stay here and be stationary on the ramp. So the idea of this is we're able to break this mg weight vector down into 2 components to help us solve problems later. And again, if you understand the geometry of it, you don't have to derive this every time. You can really just kind of jump to these conclusions, understanding this angle here is going to be theta.